You know why the computer went to the doctor? It had an overbite. That was terrible. Sorry about that. All right, in this video, we're just going to be talking about memory in embedded systems and bit operations and registers and how we access those things. So let's start with registers. Certain peripherals are mapped in system memory using registers. And actually, if you look up any sort of microcontroller in embedded system, what you're going to find is that it's going to give you a memory map for that system. And it's specifying essentially where have these things been allocated. Of course, these vary by architecture, hardware, whatever. But for the examples in this video, I'm using a particular now defunct microcontroller, but it's the one that I use in my embedded systems class, and that's an MSP 432 P401R. That's the architecture that I'm working from, but of course there are different architectures. It is an ARM-based processor, so some of the ideas will be helpful here. So in the MSP in particular, the peripherals are mapped between the hex value of 4000 underscore with, and then 4 bits of zeros, all the way up to the hex value of 5FFF underscore FFFF. I recognize you can read, but I'm still saying it out loud. So specifically the peripheral zone, it looks like this, where I've got a peripheral region, a reserved region, a bit band alias region for those peripherals, and another reserved region. So how do I specify particular registers? Well, particular registers are typically specified by a base address and an offset. So like if the base address is specified as the hex value OX2000 and you're given an offset 16H, which means the same thing as 0x16, then the actual address is just the sum of those things. So the address would be like OX2000 plus OX0016, so that's OX2016. Offsets are given in bytes. So for example, 00H is the same as 0x00. That would be the first register. That's where it's starting. 01H would be 0x01. That is 1 byte past the base. So like a byte, by the way, are 8 bits. Bytes, 8 bits. So if I have a 16-bit register, then this would be part of a 16-bit register. If I went 02H, that would be, again, 0x02. That's 2 bytes past the base. And essentially, either that's a new 16-bit register, or alternately, it could be part of a 32-bit register. So like a 32-bit register would be composed of 4 bytes. A 16-bit register is composed of 2 bytes. And so like if we were to look at this just to have a sense of how memory is working here, the address is specifying like a location in a table. I've done this with 4 bits. Obviously, you need 8 bits to make a byte. So maybe if I put 2 4-bit things together, I'd get a byte. But typically, we're saying each address is a single byte. So that would be like 8 across. And as I move forward an address, I'm just going down the stack of different registers. So examples of this for the MSP that I mentioned at the beginning of the video, if I just look at a particular set of registers, let's say the peripheral timer _ A0, the base for that is at 4000 _ 0000, and the offsets for a couple of the different parts of that register or that timer are specified in the data sheet. So you can go and look at the data sheet. It's going to tell you the base address. It's going to tell you the offset. So you can see like the control is at an offset of 00, so that's right at the start of that base. You can see like the counter at 10H, the interrupt at 2EH. Again, that H just specifying that it's a hex value. So let's actually do an example related to this. Let's say for timer A0 on the MSP 432, that's a 4, I promise. How many bytes past the base is the counter? How about the same for the interrupt vector? And what are their addresses? So based on the stuff I just had in the previous page, so let's roll up here. You'll notice that the counter is at 10H. So the counter is at 10H, which means 0x10, which means that I've got 1 times 10 to the 16th, which is equal to 16 bytes. The interrupt vector was specified to be at 2E, 0x2E. So that's 2 times 16 to the first plus 14 times 16 to the 0. That's 32 plus 14. That's 46 bytes. And of course, if you want to get their address for the counter, it's the base address, which is again 4000 _ 4 zeros, and I just add that offset to it. So plus 0x00000010. And so the address would be a hexadecimal value of 4000 _ and then 10 in a 4-bit number. That's hexadecimal 10. So that's one of my answers here. And then for the interrupt vector, I know that I'm doing the same thing, but I'm adding instead. I'm adding 2E, and so that's 0x4000 _ 002E. So pretty simple to work all of that out. In the rest of the video, we're just going to be talking about bit manipulations, which is how we're going to change values on registers or pins or anything like that for an embedded systems. And one of the key concepts we need to understand is how shift operations work. We've talked about these in other videos, but I just want to clarify it. So a shift operator, and particularly the left shift operator here, it looks something like this. One left shift by N. It creates a bit mask which has 1 at position N and 0 everywhere else. Of course, this is 0 indexed from the right. So, so if I had 0, 0, 1, 0, this would be position 0, position 1, position 2, position 3. So just remember, we're going to start counting from 0 from the right. So as an example of this, write an 8-bit binary number for 1 left shifted by 2 and 1 left shifted by 5. These are pretty quick. I'm using 0B to represent binary. So if I'm starting from the least significant bit, 0, 0, 1, and then everything else here should be 0. So that should be 1, 2, 3, 4. Okay, so that should be the first one. And then the next one, the 5th position is what looks like the 6th position total, right? So we're counting from 0. That's 0B, 0, 0, 1, 0, 0, 1, 0, 0, 0, 0. Sorry, you're going to have to listen to me say 0 and 1 a lot in this video. So that's how the shift operator works. And the reason that we use that is that when we actually start doing things with bits, the shift operator is just way quicker. So let's say we want to set a bit to a value. We would use or equals. Now I'm going to call this out a little bit here. I just want you to notice this is a bitwise or equals. If you use 2 vertical lines, that's a logical OR. That is not allowed here. We need to use a single vertical line to do bitwise ORs. So if I were to write something like this, port A OR equals 1 left shifted by 3, that's the same as saying port A is equal to port A bitwise or 1 left shifted by 3. Okay, so let's look at an example of setting a bit. For the rest of the examples in this video, I'm going to start with a fictional port B, and port B, it's currently set to be a hex value of F2. So what I want to do is first set bit 2 to be 1. What is the hex value of port B now? Okay, to solve this, what I'm going to do is first write the C code. So port B bitwise or equals 1 left shifted by 2, semicolon. That's all the code that does this. And let's just do the math. So if I were to write F2, that's 1, 1, 1, 1. We're working in binary here. 0, 0, 1, 0. And if I were to make my bit mask, it's 0B, 0, 0, 0, 0, 0, 1, 0, 0. And I'm just taking a bitwise OR of these things, which means that if either the top or the bottom have a 1 in it, we're going to get a 1. Otherwise, it's going to be 0. So the result is 0B, 1, 1, 1, 1, 0, 1, 1, 0. And if I were to write that in hex, that's F6. You can check out, when I do that quick hex conversion, you can check that out for yourself using the normal tricks you would to convert to hexadecimal. To clear a bit, we use and equals. Again, this is a bitwise and, which means a single ampersand instead of a double, which is for logical. But we also use the not, which is a tilde, to reverse the bit mask. So essentially, if we make a bit mask, which would be 1 in exactly one location and 0 everywhere else, if I take the bitwise not of that, it's going to make it 1 everywhere except for the particular bit of interest, which would be 0. Easiest way to see this is through a very quick example. So port B again is starting at F2, clear pin 5 or bit 5. What is port B now? Obviously in hex. Again, solution is pretty straightforward. The C code would be port B and equals, but then I use the logical not or tilde, 1 left shifted by 5 semicolon. So that's how you actually do that part. And then we're just doing the math out here. So first let's write the bit mask out. It's equal to 0B 0, 0, 1, 0, 1, 2, 3, 4 zeros. And if I take the not of this bitwise, it's going to be 0B 1, 1, 0, 1, 1, 1, 1, 1. And now all I have to do is AND that with the original F2 value. So that would be 0B 1, 1, 1, 1, 0, 0, 1, 0. And again, we're taking a bitwise AND. So it should only be 1 when they're both 1. So I get 0B 1, 1, 0, 1, 1, nope, false. 0, 0, 1, 0. Which of course we can do the hex calculation. That's equal to 0x d2. Okay, last operation to mention in this video is toggling a bit. We use exclusive OR equals. Exclusive OR, again, in the bitwise sense, it's the up caret. And to see what I mean by this, we're going to do an example. Port B is F2. Let's toggle bit 4. And what's port B now? And then repeat the toggle and calculation. The C code solution of this, again, is very simple. Port B exclusive OR equals 1 left shifted by 4, semicolon. So let's write this out. F2 is the same thing that it's been for all my other examples. And then my bit mask is 0, 0, 0, 1. 0, 0, 0, 0. And I'm going to exclusive OR this, which the logic for exclusive OR is if I've got A and B, then exclusive OR gives me a 1 if A is true and B is not true, or if B is true and A is not true. So in other words, if they're both 1s, I get a 0. If they're both 0s, I get a 0, and I get 1s in the other situations. So I get 0B, 1, 1, 1, 0, 0, 0, 1, 0, which of course is the hex value of E2. So that's what toggling the bit, it just changed the value of that fourth bit. If I repeat that and repeat the calculation with the same exact bit mask, now I see that I can do that exclusive OR, and I get 1, 1, 1, 1, 0, 0, 1, 0, which was the original value F2. And so by doing successive toggles, I can flip a bit on and off, which may be useful in an embedded system or code or anything like that. If you have any questions, drop in the comment. Otherwise, thanks for watching.